Welcome! In this session, we'll tackle problem number 41, first missing positive. This is a classic problem that challenges us to find the smallest positive integer missing from an array. It's a great opportunity to explore efficient problem-solving techniques. Let's dive in. In this problem, you are given an unsorted array of integers, and your task is to find the smallest missing positive integer. A positive integer is any number greater than 0, such as 1, 2, 3, and so on. The challenge is to design an algorithm that can solve this problem in linear time, or O(n), and without using any additional space beyond what is absolutely necessary. The input is an integer array called nums, which has a length n. The output is a single integer that represents the smallest positive number missing from the array. For example, if the input array is 1, 2, 0, the output should be 3. Let's take a closer look at how this works in practice. Here, for the input array 1, 2, 0, the output is 3. This is because the numbers 1 and 2 are already present in the array, so the smallest missing positive integer is 3. In another example, if the input array is 3, 4, minus 1, 1, the output is 2. Why? Because the array contains the numbers 1 and 3, but it's missing 2, which is the smallest positive integer not found in the array. These examples highlight the need to account for the presence of positive integers in the array, while also efficiently identifying the first number missing from the sequence. In the next example, if the input array is 7, 8, 9, 11, 12, the output is 1. This is because the array does not include any positive integers starting from 1 through 6. The smallest positive integer that is absent is therefore 1. This problem also comes with some constraints to keep in mind. The length of the array can be as large as 500,000 elements, and the values within the array can range from -2 billion to +2 billion. These constraints emphasize the importance of designing an efficient solution that works within these limits. Let's discuss some edge cases that you may encounter. First, if the input array is empty, such as nums equals, the output should be 1, because 1 is the smallest positive integer. Next, if the array contains only negative numbers, like nums equals, -5, -3, -1, the output is still 1, since no positive integers are present. If the array contains consecutive positive integers starting from 1, such as 1, 2, 3, 4, the output would be 5, because all numbers from 1 to 4 are accounted for, and 5 is the next missing number. Another scenario is when the array contains gaps in the sequence of positive integers, like 10, 11, 13. Here, the output is 1 because even though the numbers are large, 1 is still the smallest missing positive integer. These cases help illustrate the variety of inputs your algorithm must handle. Finally, it's important to note that the algorithm must be designed to work efficiently with very large arrays, up to a size of 500,000 elements. This means you cannot afford to use solutions that involve sorting or iterative comparisons that take more than linear time. Additionally, the solution must use constant extra space, which means you cannot use additional data structures such as hash sets or auxiliary arrays. These restrictions make the problem particularly challenging, but with the right approach, it's possible to solve it while meeting all the constraints. When approaching this problem, we first consider a few potential solutions. The brute force approach is the simplest to understand. Here, we check every positive integer starting from 1 to see if it exists in the array. This involves iterating through the array repeatedly, which makes it conceptually straightforward but computationally expensive, resulting in a time complexity of O(n squared). It also fails to meet the constant space constraint, as we're not optimizing for memory usage. While it's easy to implement, its inefficiency makes it unsuitable for this problem. Next, we have the hashing approach. This involves using a hash set to store all positive integers from the array, allowing us to efficiently check for the presence of each number. This method improves the time complexity to O(n), as lookups and insertions in a hash set are fast. However, it violates the space constraints since it requires additional memory proportional to the size of the array. Finally, we consider the cyclic sort approach. This optimized method is based on the observation that in an array of size n, the smallest missing positive integer must be within the range 1 and +1. By rearranging the elements so that each number is either in its correct position or out of range, we can solve the problem in O(n) time in O(1) space. This approach is both efficient and adheres to the problem's constraints, making it a strong candidate. Once the array has been rearranged using the cyclic sort approach, the next step is to identify the missing positive integer. To do this, we make a single pass through the array, checking for the first index I where the value at that index does not match the expected value of I plus 1. This index provides the smallest missing positive integer. If all numbers are in their correct positions, then the missing integer would be n plus 1, where n is the size of the array. The trade-offs of this approach include its ability to meet both time and space constraints, achieving O(n) time and O(1) space. However, it may feel less intuitive initially, as it involves multiple swaps to rearrange the elements. Despite this, it remains an efficient and practical solution to the problem. The cyclic sort approach is ultimately the chosen strategy for solving this problem because it fulfills all the requirements for both time and space efficiency. The key insight here is recognizing that the missing positive integer must be in the range 1 and plus 1, and rearranging the array to reflect this range allows us to find the solution with a simple linear scan. Compared to the brute force and hashing methods, the cyclic sort approach stands out for its ability to meet the constraints of O(n) time and O(1) space. While it may seem less intuitive at first due to the swapping mechanism, it avoids the inefficiency of brute force and the extra space overhead of hashing. This makes it the most effective and balanced solution for the problem, providing both optimal performance and adherence to the given constraints. The problem we're solving here is to find the smallest missing positive integer in an unsorted array of integers. For example, given an array like 3, 4, -1, 1, the smallest missing positive integer is 2. Similarly, 4, 1, 2, 0, the output is 3. This problem is particularly interesting because it challenges us to solve it efficiently, achieving O(n) time complexity while using constant extra space. To do this, we'll leverage an index-based placement approach. First, it's important to understand the problem constraints. The missing positive integer will always fall between 1 and n plus 1, where n is the size of the array. Any negative numbers or zeros are irrelevant because they don't contribute to the solution. For example, if the array has a size of 4, the output must be in the range 1, 5. This insight allows us to limit the range of numbers we care about, which is key to simplifying the solution. To begin solving the problem, the first step is to segregate non-positive numbers. Since we only care about positive integers, we can get rid of irrelevant values like zeros, negatives, or numbers greater than n. We achieve this by traversing the array and replacing any number less than or equal to 0, or greater than n, with a placeholder value such as n plus 1. This ensures that these invalid numbers won't interfere with the rest of the algorithm. Once we've done this, the second step is to use an index-based placement strategy. The idea here is to leverage the fact that the array length is n, meaning we can use the indices 0 and 1 to represent the numbers 1 and n. By marking indices corresponding to the numbers we encounter as visited, we can effectively keep track of which numbers are present. For each number x in the array, if x falls within the range 1 and n, we mark the index x1 as visited. This is typically done by negating the value at that index. Any number outside the valid range is simply ignored. After marking the indices, the next step is to identify the missing number. To do this, we traverse the array again and check for the first index I where the value is still positive. This indicates that the number I plus 1 is missing. If all indices are marked, it means the array contains all numbers from 1 to n, so the missing number must be n plus 1. Let's break this down into key insights. First, the entire approach hinges on in-place indexing, mapping numbers to their corresponding indices. This clever use of array indices eliminates the need for additional space. Second, we use negation to mark numbers as present, which is an efficient way to track values without extra data structures. Third, by replacing invalid values with n plus 1, we simplify the problem to a manageable range. Finally, it's important to handle edge cases carefully. For instance, if the array contains only negative numbers, the output will be 1, as no positive integers are present. On the other hand, if the array contains a continuous sequence of positive integers, the output will be n plus 1, the next number in the sequence. Analyzing the complexity of this algorithm, we achieve a time complexity of O(n) because we only traverse the array twice, once to segregate non-positive numbers and mark indices, and a second time to identify the missing number. The space complexity is O(1), since the algorithm operates in place without using additional data structures. Now let's walk through an example to solidify the concepts. Consider the input array 3, 4, -1, 1. In the first step, we replace invalid values, resulting in 3, 4, 5, 1. Next, we apply the index-based placement. For the number 3, we mark index 2, corresponding to 3 to 1. For the number 4, we mark index 3. The number 5 is ignored as it's out of range, and for the number 1, we mark index 0. The array now becomes -3, 4, -5, -1. Finally, in the last step, we traverse the array to find the first unmarked index. Here, index 1 is still positive, which means the missing number is 2. Let's go through another example to reinforce our understanding. Take the input array 1, 2, 0. In the segregation step, we replace invalid values, transforming the array into 1, 2, 4. Now, for the index-based placement, we start with the number 1 and mark index 0, 1 to 1. Next, for the number 2, we mark index 1, 2 to 1. The number 4 is ignored since it's out of range. At this point, the array becomes -1, -2, 4. In the final step, we traverse the array to find the first unmarked index. Index 2 is still positive, indicating that the missing number is 3. This example highlights how the algorithm handles edge cases like numbers outside the valid range and ensures we efficiently identify the smallest missing positive integer in all scenarios. This implementation solves the first missing positive problem in O(n) time in O(1) space. Here's the step-by-step explanation of the code. 1. Initialization *. First, we determine the length of the input array nums and store it in n. This is necessary to handle bounds effectively. 2. Step 1. Preprocessing. Replace all numbers that are non-positive, less than or equal to 0, or greater than n with n plus 1. Since the missing positive integer must be in the range 1, n plus 1, these out-of-bound values are irrelevant and can be ignored during the marking process. 3. Step 2. Mark presence. Use the array indices as a hash map to mark the presence of numbers. For each number in the array, compute its absolute value, val. If val is within the range 1 is yin, mark its presence by negating the value at the index val 1. Negating ensures that the value at that index is marked as visited while preserving its magnitude. For step 3, find missing. Iterate through the modified array to find the first positive number, which indicates the smallest missing positive integer. If nums I 0 at index I, it means I plus 1 is the missing number. 5. Edge case * if all numbers from 1 to n are present, i.e., no positive numbers are found in the final array, the smallest missing positive integer is n plus 1. This approach ensures we do not use any extra space and examine each element of the array at most twice, achieving O(n) time complexity. The key insight is leveraging the array indices as a hash map, which eliminates the need for additional data structures. Here, we begin implementing the solution in Java. The goal is to find the first missing positive integer in the input array. First, we determine the length of the array, which helps us define the range of valid numbers we are considering. Since the problem focuses on positive integers from 1 to n, we need to eliminate any numbers that are non-positive or exceed n. To do this, we iterate through the array and replace these invalid values with n plus 1, a number outside the valid range. Next, we use the indices of the array as a hashing mechanism to track the presence of numbers. For each element in the array, we take its absolute value, check if it falls within the valid range, and then mark its corresponding index by making the value at that index negative. This marking process ensures that we track which numbers from 1 to n are present without using additional space. Finally, we prepare to identify the first missing positive integer by examining the modified array. After marking the presence of numbers, we loop through the array one last time. The first index that contains a positive value indicates the smallest positive integer that is missing. Since our marking process used negative values to denote presence, any index with a positive value means the corresponding number was not encountered. We return the index plus 1, as array indices are zero-based. If all indices are marked, meaning all numbers from 1 to n are present, the missing number must be n plus 1. This ensures the solution handles all possible cases efficiently. The implementation is complete, and it runs in O(n) time while using O(1) extra space, meeting the problem's constraints. Let's start with the example where nums is 3, 4, minus 1, 1. In the first step, we replace any number that is non-positive or greater than n, where n is the length of the array. Since n equals 4 here, we replace all numbers less than or equal to 0 or greater than 4 with n plus 1, which is 5. For instance, nums 2 is minus 1, which is less than or equal to 0, so we replace it with 5. After processing all elements, the array becomes 3, 4, 5, 1. Next, we mark the presence of numbers using the indices of the array as a hash. For each number, we calculate its absolute value, use it to find the corresponding index in the array, and negate the number at that index to indicate that the value exists. Starting with I equals 0 and val equals 3, we mark nums 2 by negating it, resulting in 3, 4, minus 5, 1. At I equals 1, val equals 4, so we mark nums 3, which becomes 3, 4, minus 5, minus 1. At I equals 2, val equals 5, but since it is greater than n, we skip it. Finally, at I equals 3, val equals 1, we mark nums 0, giving us the final state for this step, 3, 4, minus 5, minus 1. Now, in the last step for this example, we identify the first missing positive. To do this, we traverse the array and look for the first index I where the number at that index is still positive. Starting with I equals 0, nums 0 is minus 3, so we skip it. At I equals 1, nums 1 is 4, which is positive, meaning the first missing positive number is I plus 1, or 2. For the second example, nums is 1, 2, 0. In the first step, we again replace numbers that are non-positive or out of bounds. Here, n is 3, so we replace numbers less than or equal to 0 or greater than 3 with n plus 1, which is 4. Nums 2 is 0, so we replace it with 4. After this step, the array becomes 1, 2, 4. Next, we follow the same procedure to mark the presence of numbers using the indices as a hash. Starting at I equals 0, val equals 1, so we mark nums 0 by negating it, resulting in 1, 2, 4. At I equals 1, val equals 2, we mark nums 1, giving us 1, minus 2, 4. At I equals 2, val equals 4, but since it is greater than n, we skip it. The array remains 1, minus 2, 4. To identify the first missing positive, we traverse the array and look for the first index I where nums I is positive. At I equals 0, nums 0 is minus 1, so we skip it. At I equals 1, nums 1 is minus 2, so we skip that as well. At I equals 2, nums 2 is 4, which is positive. Therefore, the first missing positive is I plus 1, or 3. Finally, let's consider the third example where nums is 7, 8, 9, 11, 12. Here, n is 5, and in the first step, we replace all numbers less than or equal to 0 or greater than n with n plus 1, which is 6. Since all the numbers in the array are greater than n, we replace every element with 6. The array becomes 6, 6, 6, 6, 6. For the second step, we attempt to mark numbers using the indices as a hash, but since all numbers are 6, which is greater than n, no changes are made, and the array remains 6, 6, 6, 6, 6. In the final step, we look for the first index I where nums I is positive. Here, all numbers are positive, so the smallest missing positive is n plus 1, which is 6. The time complexity of this solution is O(n), and we can break it down into 3 distinct steps. In the first step, we iterate through the array to replace all non-positive and out-of-bound numbers. This involves a single for loop that runs n times, where n is the size of the input array. For each iteration, we perform simple constant time operations like checking conditions and modifying elements. As a result, this step takes O(n) time. Next, in the second step, we use the array itself to mark the presence of numbers. Here, another for loop goes through the array, and for each element, we calculate its absolute value and mark the corresponding index as negative, provided it's within bounds. Each marking operation is done in constant time, so this step also contributes O(n) time. Finally, in the third step, we identify the first missing positive number. This involves yet another for loop that scans the array to find the first positive value, with each check taking constant time. Again, this step adds O, n, to the total. So overall, the time complexity is O, n, for each step, leading to an aggregate complexity of O, n. When we combine all three steps, the total time complexity remains O, n, because O, n, plus O, n, plus O, n, simplifies to O, n. This means the algorithm processes the array in a constant number of linear passes, making it highly efficient. Now, moving to space complexity, the solution achieves O1, because it modifies the input array in place to mark the presence of elements. This eliminates the need for additional data structures like hash sets or auxiliary arrays. The only extra space used is for a few fixed variables, such as the loop counters and temporary values, which do not depend on the size of the input. Since there is no additional memory requirement that scales with the size of the array, the space complexity is constant, or O1. Let's compare this optimized approach to the brute force solutions. A naive method might involve sorting the array first, which has a time complexity of O, n log n, followed by a linear scan to find the missing number. Alternatively, using a hash set to store the elements and check for the smallest missing number would achieve O, n, time but at the cost of O, n, space. However, our optimized approach improves on both fronts, achieving O, n, time complexity and O, 1, space complexity. It does this by leveraging the input array itself as a hash table, avoiding the need for additional storage. Looking at the best, average, and worst-case scenarios, the algorithm consistently performs O, n, operations. Even in the best case, where the array already contains all integers from 1 to n, 3 passes through the array are still required. For average cases, with random arrays containing mixed values, the time complexity remains O, n. And in the worst case, with arrays full of large, out-of-bound values or negative numbers, the algorithm still processes the input in linear time. Finally, let's solidify our understanding with a mathematical proof for the big O analysis. Each of the three loops in the algorithm runs at most n iterations, where n is the size of the array. Within each iteration, operations like comparisons, computing the absolute value, and accessing or modifying array elements are all constant time operations. This means that the total time spent in each loop is proportional to n, and summing up the contributions of all three loops still results in O, n, time complexity. On the space complexity side, the algorithm uses no extra space beyond the input array and a small number of fixed variables. Since the memory usage does not grow with the size of the input, the space complexity is constant, or O1. Together, these analyses confirm that the solution is both time-efficient and space-efficient, making it optimal for this problem. When solving this problem, there are several common mistakes to watch out for. First, edge cases like empty arrays or arrays missing the smallest positive integer, which is 1, can lead to incorrect results if not properly handled. Always validate these specific scenarios. Another frequent pitfall is using nested loops unnecessarily, which results in an inefficient O, n squared, time complexity. This approach may work for small inputs, but it will fail to scale for larger arrays. Additionally, directly modifying the original array can introduce unexpected behavior, especially if the array needs to remain intact for other operations. Instead, consider using a copy of the array or a separate data structure. It's also important to ensure your solution skips over irrelevant values like negative numbers and zeros, as they don't contribute to the goal of finding the smallest positive integer. Finally, in languages like C++ or Java, be mindful of the potential for integer overflow when working with large indices or values. Always check the constraints and use data types that can handle the required range. Now, let's focus on insights that are particularly relevant for interviews. A key aspect of this problem is optimizing from a brute force approach to a linear time solution. This typically involves leveraging array properties, such as using indices as markers, to reduce complexity. It's also valuable to recognize that this problem is part of a broader class of problems dealing with missing or duplicate numbers. Mastering this type of problem can help you solve variations like finding duplicates or identifying missing ranges. During interviews, your ability to communicate your thought process is critical. Start by explaining the brute force approach, pointing out its inefficiencies, and then guide the interviewer through your thought process as you refine the solution. Finally, be aware of the trade-offs involved. While the most efficient solutions achieve O(n) time and O(1) space by modifying the array in place, there are cases where constraints prohibit altering the input. In such cases, you may need to opt for an O(n) time and O(n) space solution using a hash set instead. There are also several related problems that build on similar concepts. The first, of course, is the core problem itself, LeetCode 41, first missing positive, which focuses on identifying the smallest missing number. Another closely related problem is LeetCode 448, find all numbers disappeared in an array, which involves finding missing numbers within a given range. Additionally, LeetCode 287, find the duplicate number, is similar but shifts the focus to locating duplicates rather than missing values. Finally, LeetCode 442, find all duplicates in an array, is another related problem that involves identifying duplicates in an array. By practicing these problems, you'll gain a deeper understanding of the patterns and techniques required to solve this class of challenges effectively. Let's review some alternative approaches to solving this problem. The hash set approach involves storing all elements of the array in a hash set, then iterating from 1 onward to find the first missing positive integer. While straightforward, it uses O(n) time and O(n) space. Another method is the in-place index marking approach, where you modify the array by marking indices corresponding to the values within the array. For example, you can negate the value at the index that represents a number. This achieves O(n) time and O(1) space but alters the input array. A simpler, though less optimal, approach is sorting the array and iterating to find the missing integer. This method runs in O(n) log n time and is easier to implement but is not as efficient as other solutions. Finally, for problems with bounded constraints, you could use bit masks or Boolean arrays to track the presence of numbers. This approach is efficient for small ranges, running in O(n) time and O(n) space, but it's limited by the maximum allowable range. Great job! In this session, we solved first missing positive using an efficient algorithm. We discussed the trade-offs, key concepts, and tips for tackling similar problems. Don't forget to practice and refine your skills. Thanks for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!